Good afternoon, everyone. My name is Jiannan Wang, and I'm a research scientist on the PyTorch team at Meta. Today, I'm excited to talk about how we can unlock new levels of performance in PyTorch by leveraging large language models to streamline GPU kernel development. Let me start with a very brief primer on GPU kernels. GPU kernels are essentially small programs that run on the GPU, and they are the backbone of high-performance computing in deep learning. They are responsible for executing the core mathematical operation that power the neural networks. There are several approaches to GPU kernel development with a natural trade-off between efficiency and development efforts. For example, CUDA gives you fine-grained control over memory utilization and hardware hierarchies. This means you can squeeze out the highest possible efficiency, but it comes at a cost. You often need to tune each operator and sometimes each input shape by hand. This process can be time-consuming, and the resulting code is often not portable across different hardware. On the other end, Torch compile allows for very fast research iteration. You can quickly prototype new ideas, and the compiler takes care of parallelism and scheduling for you. The trade-off here is that you have less ability to fine-tune performance. There's smaller room to improve if you need to optimize for a specific use case. Sitting between these are datasets like Triton and CUDA. They offer a balance between productivity and performance, giving you more control than high-level abstractions, but with less complexity than raw CUDA. Each of these DSLs strikes at different balance, so you can choose the right tool for your need. Here's a more concrete example. Torch compile does most optimization for you under the hood. It provides high research iteration speed with a relatively low optimization potential. Triton gives you users control over the memory layout on GPU through tiling, allowing to optimize for specific workloads and hardware. QDSL lets you explicit control over threads, warps, memory hierarchy, and epilogue, providing a high optimization potential. In summary, as you move from Torch compile to Triton to QDSL, you gain more control and optimization potential, but you also take on more complexity and development work. Optimizing GPU kernels can lead to substantial performance gains. For example, Quark shows how different kernel development approaches impact speed. By understanding and exploiting the thread and memory hierarchies on modern accelerators, the kernel performance can get close to speed of light. Given that writing highly optimized GPU kernels offers tremendous performance potential, but it's also slow and labor-intensive, we ask the following question. Can we leverage large language models to automate and accelerate the kernel authoring process? The idea is to use LLMs to generate GPU kernels that are correct and both optimized for modern hardware. There's a lot of exciting activities happening in the field right now, both in academia and industry. On the evaluation side, we have benchmarks like KernelBench from Stanford and TritonBench from Tianjin University and Harbin Institute of Technology. These benchmarks provide standardized way to measure the correctness and performance of LLM-generated GPU kernels. On the agent side, here are a number of research groups and independent contributors building LLM-powered agents for kernel generation and optimization, include Mako, Meter, Sakana, independent researchers, Standard Kernel, Cognition, and many others. One of the most important lessons we've learned is that benchmarking is the key to empowering LLM-driven kernel authoring. Benchmarks provide us with objective, standardized measures of both correctness and performance. Without them, it's nearly impossible to know if an LLM-generated kernel is actually working as intended, or if it's truly delivering the speed up we are aiming for. While there's a lot of effort to use LLMs for GPU kernel generation, the reality is that doing this correctly is extremely hard. One common pitfall is forgetting to clear the GPU cache before running your benchmarks. If you skip that step, you might end up measuring only the kernel launch overhead rather than the actual runtime performance of your code. This can lead to misleading results where a kernel appears to be fast simply because the cache was already primed or because the measurement didn't include the full execution path. One important takeaway from our experience is that the claims of 10 times speed up from AI-generated kernels often signal that something is off in the comparison. In many cases, these dramatic speedups happen because the baseline is not a fair one. For example, you might be comparing a highly optimized kernel against a completely unoptimized or naive implementation. Or as we discussed earlier, you might be measuring performance indirectly. The reality is, once you are comparing well-optimized kernels on a level playing field, true 10 times speedup is extremely rare. So whenever you see the huge speedup numbers, it's worth digging deep to understand what's really being compared. To address these challenges and make the evaluation of LLM-generated GPU kernels more reliable, we developed Backend Bench. Backend Bench is our evaluation suite for testing how well both LLMs and humans can write PyTorch backends. Here's what Backend Bench brings to the table. We leverage PyTorch's op-info test suite for comprehensive edge case correction testing. Instead of relying on artificial or toy examples, Backend Bench uses real tensor shapes from Hugging Face models. You can pip install Backend Bench and use the generated kernels directly in real models. This makes it easy for researchers and engineers to try out new kernels and see how they perform in reality. Right now, Backend Bench supports both Triton and CUDA, and we are working to add even more. This flexibility lets you evaluate kernel written in different styles and languages, all within the same framework. One of the core principles behind Backend Bench is our aggressive focus on correctness. We focus on PyTorch operator set, which has stood the test for nearly 30 years. We put a lot of effort into engineering away most correctness issues right in the evaluation process. We also make it a priority to audit results and present them in a way that makes debugging straightforward. And finally, we ensure that the solutions we evaluate are mergeable into PyTorch. This is important because if a kernel is good enough to be merged into PyTorch, we believe it's a strong signal that it meets the highest standard for correctness. I want to emphasize again that correctness in kernel generation is fundamentally hard. There are some of the reasons, like there are operator variants. Each operator in PyTorch, like torch_add, must handle multiple data types, and they must support broadcasting, in-place operators, pre-allocated outputs, and scaling factors. The kernels also need to handle edge cases, including NAN, infinity, zero-size tensors, and extreme cases. And the difference in hardware, like subtle floating point behaviors, can vary across different GPUs, which must be handled by, which brings challenge to the kernel authoring. And it's also important to test with tensor shapes from actual models, not just synthetic or toy sizes. Sometimes the kernel produces results that looks plausible but are actually incorrect. And there are other PyTorch footguns that can lead to misleading results. When benchmarking GPU kernels, the footguns can lead to misleading or inaccurate performance results. And here we are sharing some of the common footguns. First, sometimes people forgot to clear the cache or warm up when benchmarking performance. That leads to just measuring the launch overhead, not the actual computation time. To avoid this pitfall, we recommend just use Triton testing to bench for performance benchmarking. Another footgun in benchmark and testing GPU kernels is the use of input distribution that can unintentionally trivialize the testing. If you benchmark a mean kernel using a large vector sampled from a normal distribution with mean 0 and variance 1, the average will almost always be 0. This opens the door for a super smart but actually incorrect kernel that simply returns 0 for any input. Such a kernel would pass the assertion test. However, it would also would be the fastest possible implementation because it skips all the computation. However, it is just wrong. To ensure our kernels are both correct and robust, it's crucial to test them with a diverse set of inputs. We use op-info, the same comprehensive test suite that PyTorch has developed and refined over the past 9 years. It catches edge cases that can break custom kernels but are handled correctly by PyTorch, including tensors of size 0, 1, NAN, and infinity values and mixed data types and broadcasting each cases. Most custom kernels will crash or behave incorrectly for those kernels in this situation, but PyTorch standard operators will not. And this is the bar we set for merging new code into PyTorch. We also avoid testing shapes that are too small, since they most likely measure launch overhead rather than the actual kernel performance. Instead, we focus on useful, realistic shapes. We trace the models used in PyTorch CI systems, like the Hugging Face models. We record the tensor shapes from the real models and use them in our testing. By combining op-info and tracing real models, we've built a diverse set of tests for our GPU kernels. The last footnote is that the LLMs sometimes cheat during kernel generation tasks by simply calling the original PyTorch operators instead of generating a new kernel implementation. This fallback is difficult to detect because output appears correct, but the LLMs are just not producing a new kernel. Our solution is to override the operator by itself. If the LLMs tries to fall back to the original operator, it triggers an infinite recursion error. And here is the structure we use to submit the kernels. We use a directly based structure for submitting LLM-generated kernel implementation. LLM researchers will drop kernel implementation into folders. Each file then gets loaded to override a torch operator. This is how the eval team of backend bench interact with meta researchers. And here are our results. So we have some correctness results by asking Cloud n times. With a simple agent retry loop with feedback with Cloud, we can get about 53% of PyTorch operators implemented in Triton. Thanks to Shaheen for making this happen, and thanks to Sahan for making it easy to use. We also generated 84 kernel examples, all available for you to review in our backend bench repo. What's really interesting is that some of these LLM-generated kernels are starting to show advanced behaviors, like promoting calculation to FP32 in the middle of a computation, which improves numerical accuracy. When we benchmark these kernels, most of them perform at 70 to 100% of PyTorch's baseline, and a few even outperform PyTorch by up to 20%. Thanks to Laura for getting those kernels with LLM. We also performed an end-to-end convergence testing on NanoGPT. We use LLM-generated kernels for the forward pass on several important PyTorch operators. But for the backward pass, we had to fall back to PyTorch eager mode because the LLM-generated kernels are just not reliable enough yet. This demonstrates that LLMs can successfully generate kernels for a diverse set of operations in real model. While we see promising results in model convergence testing, the performance of these kernels is still not optimal. There's a clear gap between what LLMs can generate today and the highly tuned human-written kernels that we rely on for production workloads. There's still a long way to go. And in the end, I want to thank all the contributors to Backend Bench. And thank you to Manhost for helping the community to be more correct. Thanks Annie, Simon, and Alex for prompting us how to get LLM-generated kernels into PyTorch. We are looking for more contributors to add support for more DSLs and add training and distributed operator support, and to add more backend extension system. Please reach out to us if you are interested on the Discord GPU mode on the Popcorn channel. And the QR code is linked to our backend bench GitHub repo. Thank you very much. Yes.
Is this a suite of basically tensor shapes, or like is this set of benchmarks a specific set of operators, and that's what you evaluate, or is it any operator but it'll generate the most useful set of tensor shapes for an operator?
That's a good question. So currently we focus on the PyTorch's core operators, but we plan to add support for example, operator fusions. The reason we focus on the PyTorch ATON the core operators is because we believe those operators have been tested for many years. Those operators are like coming from NumPy, and that's already a very old project. We believe that instead of reinvent those operators, we can just start from that. And that's the operator set we choose for this project. But we are going to add, for example, operator fusion in the future.
Thank you.
Yes.
Hi. Could you please tell me a little bit about your floating point testing regime, in particular testing for nans and things like that? How do you make sure that nans and other exceptional values are caught properly in the generated tests?
All right. For that, because we are using the op-info, that's the one reason we use the op-info. Op-info is a PyTorch testing suite that used by PyTorch to develop the test for the operators, and we reuse that part to generate inputs for the operators, and that's one source of our input generation. The other source of our generation is the sorry, where is that? Another source of our generation is that we traced the real shape from Hugging Face models, so that we use the input shapes from the real Hugging Face models, so that our test will be in a realistic situation. So that's the two principles we use to form our input shape testing. Thanks.
I have a few questions as well. During the performance evaluation, do you also account for GPU throttling and effects like that?
Sorry, I didn't quite get your question.
During the performance evaluation, do you also account for GPU throttling? Like that GPU drops frequency if you benchmark too much, stuff like that?
Sorry, I didn't quite get your question, but currently we are testing operator by operator. So yeah.
But do you also evaluate performance, right? You take a look how long a kernel took to run.
Oh, you mean our kernel agent? Sorry, what?
Yep. Hello. Okay.
In the cases where the kernels generated were faster than the PyTorch ops, what exactly was the LLM doing that was making it better? Like, what did it find that the handwritten kernels didn't have?
Yeah, that's a good question. So oh, okay. Sorry that I cannot give you an answer right now, but if you're interested, we have provided the link to the kernels inside, and if you're interested, I can talk. I can review those kernels and talk to you later.
Thank you.
Yeah, what kind of relative tolerance and ATOL are we having for the kernels that we are testing? The tolerance that we have, how much numerical difference do we allow? Okay, can you hear me?
Sorry, sorry, I can hear you, but I do not quite get your question. Are you asking the problem we do with those operators?
The numerical difference. So how much tolerance do we have? So is it? Yeah.
The numerical tolerance. I believe currently we set to relatively that's the standard we use in PyTorch.